Okay, folks, so this supplemental lecture is going to cover radical chemistry. We're going to talk about stability. We're going to talk about reactivity, primarily in one context. But before we get into all that, I do want to cover the arrow pushing convention for radical chemistry. So up to this point, you folks have been doing electron pushing with arrows using double-bladed arrows. Okay, when you have two blades on the head of the arrow, okay. The reason you have two blades on the arrow is because it represents the movement of two electrons, all right? When we talk about radicals, the arrow pushing involved uses single-bladed arrows that look like this. Okay, so hopefully that makes sense, and I'll show you examples of the difference right now, because we're going to talk about heterolytic versus homolytic bond cleavage. Okay, so bond cleavage is the same thing as bond breaking. Okay, so heterolytic bond cleavage is what you guys have been drawing with your double-bladed arrows since you started pushing electrons. Okay, so here I've used a double-bladed arrow to show a heterolytic cleavage of a CH bond in methane. Okay, so both of the electrons from the bond between carbon and hydrogen are going to carbon and abandoning hydrogen, which is going to give us something like this. Okay, so now the pair of electrons that was in the bond is now a lone pair on carbon, which has a negative charge, and hydrogen has no electrons, so it is a positive charge or a proton. Okay. Homolytic cleavage looks like this. Okay, the homo means same, and so homolytic cleavage is when each atom gets the same number of electrons. Okay, so you get one electron going to hydrogen, you get one electron going to carbon. That gives you a methyl radical, shown here, and a hydrogen radical. Okay, so hopefully that makes sense. Both cleavages involve two electrons moving, right? It's just one involves the electrons moving all in the same place, okay? And then these arrows indicate one electron moving in the indicated direction. So hopefully that makes sense. This is a table of bond dissociation enthalpies, or bond dissociation energies, really. So these are delta H values for a bond breaking or dissociating, right? So you could think of two atoms bound to each other as being associated with one another. When that bond breaks, they are disassociating from one another, so the bond is breaking. I want to point out three particular values on this chart. So again, this chart is experimental data that's been compiled for this book. Probably for a journal article somewhere in this book is borrowed it. Okay, but we're focusing on the CH group, or the CH bond from a primary carbon here. Okay, the CH bond at the secondary carbon of propane, which is here, and then the CH bond at the tertiary carbon in 2-methylpropane, which is a constitutional isomer of butane. Okay. So here that data has been compiled. We see what these energies describe. They describe the energy required to homolytically cleave a given bond. Okay, so you'll notice that it takes the most energy to break the CH bond from a primary carbon. Okay, the reason for this is because a primary radical, the product, is going to be more unstable, higher in energy, more reactive. Okay, so it takes more energy to create that species. Therefore, it should come as no surprise that it takes the least amount of energy to form a lower energy or more stable radical from a tertiary carbon CH bond, okay, shown here. Okay, so we've talked about this in class a little bit. just to reiterate, so radicals are similar to carbocations in lots of ways. The first way is that they are electron deficient. Okay, they are not charged. They don't have a formal positive charge, and yet they have an unfilled octet or unfilled valence shell. Okay, so these things want that full valence. They want electrons. So they are reactive, they just aren't charged. Okay. Another similarity, they are sp2 hybridized. The difference being that in the p orbital, instead of having no electrons, which is the case in carbocations, now the unpaired electron of the radical species lives in that p orbital. So there is an electron in the p orbital, but it's not filled. Okay. They are stabilized by hyperconjugation just the way cations are, carbocations are. And hopefully that comes as no surprise because, again, hyperconjugation has to do with that sort of fleeting electron orbital overlap as you rotate about bonds on carbon that are substituted on the carbon that has the radical or the carbocation. So again, more substitution means more stable for both radicals and carbocations. Okay. The relative stability of carbon radicals, as we've already talked about, it's exactly like carbocations. Tertiary radicals more stable than secondary, more stable than primary. Okay. Another key difference here is that primary radicals can exist. Okay. I told you, and this is something that you should definitely take note of if you haven't already, that primary carbocations, as far as introductory organic chemistry is concerned, do not exist. Okay? So hopefully that all makes sense. If you have questions on this, please come talk to me or ask me, son. So something else that you should do is think about how the iShares effects will affect the stability of radicals. You have a table from lecture, hopefully that you wrote down, addressing how these effects can stabilize or destabilize anions and carbocations. Now I'd like you to think about how they affect radicals. Okay.